Okay, welcome back. This morning here at the Weather and Climate Summit in Breckenridge, our first speaker is Dr. Jennifer Francis from Rutgers University. Let's take a look at a little video so you can get familiar with Jennifer right before her presentation.
I'm a research professor at Rutgers University in the Marine and Coastal Sciences Department, and that's in New Brunswick, New Jersey. So I got into using satellite information to study the atmosphere, mostly over the sea ice in the Arctic, and how it's changing, how it interacts with the sea ice, the clouds, the water vapor in the atmosphere, the temperature profiles, all from satellites. My research lately in the last few years has really been more about how Arctic change, and particularly Arctic amplification, which is the enhanced change in the Arctic, is going to be felt down here at mid-latitudes. The Arctic paradox has been coined to describe this notion that we've got all this warming happening in the Arctic, and yet the last couple of winters have been extremely cold and snowy both in Europe and along the East Coast.
And now scientists are questioning, is this recent Arctic outbreak, or at least this big surge of cold air, related to climate change in some way?
I think it's extremely important that television meteorologists are up to date in the current research in weather and climate and so forth. I think they have a huge role to play in connecting with the public and being able to explain some of the phenomena that they're hearing about from Congress people, in the newspapers. I mean, there's so much bad information out there, and I think they can play a huge role in setting the record straight so the public has a good understanding of what some of this research coming out really means. Sometimes it sounds contradictory. For example, the Arctic paradox. People will say, well, the Arctic's warming and yet the winter's so cold, those scientists don't know what they're talking about. But if you've got a TV meteorologist who can stand up there and say, well, actually, it does make sense and here's why. I think it's very, very important because they are, in some ways, the only scientists that a lot of people ever listen to. Okay, well, good morning, everyone, and thank you so much for hanging in here till Friday and up so early this morning. And I especially want to thank Jim White and Dave Jones for asking me to be here this week. It's been an absolutely phenomenal week. I've met some incredible people, and it's just been terrific. So, as my introductory little video said, I've been asked to talk about this concept of the Arctic paradox, and I've been doing quite a bit of research on this just very lately. It's a very new topic. There really hasn't been much done about it before. And actually, I think there's a whole lot more to the story than just the Arctic paradox. And so I've actually changed my title. Is this working? Not very well. Okay, well, I'll go to the buttons. So my new title is The Arctic Sea Ice, A Tragic Tale of Loss and Revenge. All right, so I think I'm going to have enough time for questions. We don't have a question and answer session set up this afternoon, so if you have any questions as I'm going along, please lob them up here and I'll try to take care of them. And I think we'll also have some time at the end, so please don't hesitate to speak up. So I want to start out by bringing you back to what we Arctic scientists call the good old days. These good old days were when we could look down from space with our satellites down onto the Arctic Ocean. Here's Greenland here, here's North America, Alaska, and Eurasia over on that side. And we could look down and see all this, what's colored here in pink, which is the sea ice that's floating on top of the Arctic Ocean. Back in 1980, for example, which is what we're showing here, at the end of summer, Summer, at the end of summer is when the Arctic sea ice is at its minimum extent, which is what's being shown here. The ice was nice and thick, it was healthy, it had filled up the whole Arctic Ocean. But that is not what we're seeing these days. These days, it looks more like this. This is from September 2007. You can just see with your eye, there's just this huge chunk taken out of the sea ice extent. In fact, the difference is about 40%. A 40% loss in the amount of sea ice in the Arctic. And in terms of area, that is about equal to 1.3 million square miles of ice that's been lost just in the last few decades, 1980 to 2007. So that's a big area. Let's put it in context in terms of space that we know. It's equivalent to about 42% of the lower 48 of the US and all of Europe. It's a huge amount of ice that's been lost. So that leads us to this question. That is not whether sea ice is affecting large-scale atmospheric circulation. It's how can it not? It is such a huge change in the Earth's system. But I want to back up a little bit first and try to explain how we got ourselves into this mess. All right, so this is a graph showing Arctic sea ice extent. It's from the Cryosphere Today. It's a wonderful website that Bill Chapman's group at University of Illinois puts out there. And he tracks the sea ice extent, in this case going all the way back to 1900. So this is going back pretty far in time. Of course, back in this range of time, we didn't have satellites flying. So some of these data are not as reliable as they are now, but they're still very useful. And what you can see is these different curves are for different seasons. The ones on top are for the winter time, which of course is when we have more ice in the Arctic. And the green line there is for summer, when the sea ice is at its minimum extent. And what you notice is that, yeah, there's a lot of wiggles from year to year, but basically it's pretty steady. The amount of ice in the Arctic was quite steady during this time period. And I think if there had been any big changes, we would have seen it, because back in this time period, there were a lot of whale boats up there. There were a lot of other kinds of ships. There were people up there. So we would have known if there was a big decrease in the ice. So as we go forward in time now, starting in the 50s, something very different started to happen. And you can see that in all seasons, and especially in the summertime, we start to see this really dramatic decline in the amount of sea ice extent. And then just in the last decade, this decline has accelerated dramatically in all seasons, and again, particularly in the summertime. So the story goes like this. Going back again to the good old days, we've got Alaska over here. This is the Bering Strait and Siberia. Here's northern Canada and Greenland over there. This is how it looked back in the good old days. Lots of nice thick ice. And beginning about in 1950 or so was the beginning of the Industrial Revolution. We started to pump a whole lot of carbon dioxide into the atmosphere. So we've got all these greenhouse gases in the atmosphere increasing every year. And in conjunction with that, we see that there's more water vapor in the atmosphere as well as the globe warms in general. That water vapor gets transported up to the Arctic, where it acts as another greenhouse gas. It also forms more clouds, and all of those things combined are radiating more infrared radiation from the atmosphere down to the surface and gradually thinning the ice cover over time. And we can see that this is happening. We have observations of the thickness of the ice cover. These black bars here are measurements or estimates of ice thickness that are taken from submarines that were traveling under the ice cover. These are Navy submarines. They're looking up with a sonar, and by measuring the depth of the keels or the depth of the ice below, you can make estimates of what the total ice thickness is. So these are just different areas across the Arctic basin and the ice thickness. And you can see those black bars are roughly around 3 meters. That's a typical ice thickness over the Arctic Ocean during the good old days. But as you move into the 90s, which are the red bars, you can see that the ice thickness has decreased by about, again, 40%. And even in the most recent decade, the blue bars, you see that the ice thickness is continuing this downward trend.
Has there been calibration between the ISAT measurements and the old sub-measurements?
Yes.
Can you repeat that?
Yes. The question was whether there's been some calibration between what the submarines have measured and the newer satellite estimates from ISAT. And yes, they have been intercalibrated, and they both are telling the same story. In fact, I think I have an ISAT data point here for you. All right. So when the ice was nice and thick, the variations that we saw from year to year were mostly caused by changes in the wind patterns. The ice was too thick to melt in any given season, so there really wasn't a lot of total melt going on. Any of those variations were really just being moved around a little bit by the wind. But you remember back to that first graphic that showed between 1900 and 1950 or so, it was pretty steady. So, you know, the winds would change, but the ice really didn't respond very much. But now that the ice is so much thinner, it is responding a lot more to any variations in the wind patterns. And in fact, back in the 1990s, in the early 1990s, we had this period of the winter when the Arctic Oscillation Index had this several years in a row when it was very, very positive. So this is the Arctic Oscillation Index starting way back in 1950 till present, and you see that period of time back in the 90s when the AO was in a very positive phase. So what does that mean for the ice? Well, in normal atmospheric conditions, which is shown up here, and you can see there's Greenland here, this is Alaska, the northern coast of Canada. The Arctic Ocean was typically covered by a large high pressure over on the Pacific side of the Arctic, and this acted to circulate the ice around and around the Pacific side of the Arctic Ocean. And so it spent a lot of time, years in fact, circulating around the Arctic Ocean, and so it would just get thicker and thicker, and it would build up against the Canadian coast, and it would eventually, some of it would get transported out by the winds into the North Atlantic. But what happens in a positive AO phase is that high pressure weakens dramatically, and so the trajectory of the winds now takes the ice much more directly out into the Arctic Ocean. It doesn't spend much time circulating around over on the Pacific sector there. And I have a video that I hope is going to work to illustrate this point. There we go. See if we can get that to go. Mm-hmm. Okay, stop.
Click that.
Right there. Okay, and I'll bring it back.
Drag it. You can drag. Just click here and drag that back.
Okay. Got it. Except it didn't do it.
See, stop. And then play, then pause.
Okay. Okay. So I've got a video to show you here. This is taken from NOAA's Climate Watch website, and the data are actually developed by a group at the National Snow and Ice Data Center here in Boulder, Colorado, Jim Maslanik and Chuck Fowler's group. And what this is showing you is, here we are again in the Arctic Ocean. We've got the land masses labeled. The white stuff that you can see in the middle of the ocean here is the ice that's over 9 years old. So it's been spending a lot of time circulating around in the in the Pacific sector over here. And as you go up into the bluer shades, the ice gets younger and younger. This has been measured using passive microwave satellites. And what they can do is actually identify features in the sea ice and then track them over time and estimate how old each piece of ice really is. So we've got, starting in 1987 here, you can see that there's a lot of old ice in the Arctic Ocean. It tends to be packed up against the Canadian coast, and the ice gets thinner and thinner as you go out to the Siberian side. So what you're going to see as the time moves on in this video is a pulsing of especially these very young ice types as the seasons progress. So in the winter it grows, and in the summer it melts back. So that's what you're going to see. All right, and starting, you can see the date here. We're still in the 1980s, and as I told you, the positive AO kicked in, and you can see how that thick ice is being driven right out into the Atlantic Ocean. There's less and less of the old ice now. We're here still in the 1990s. And as that AO continues to drive all the thick ice out of the Arctic Ocean, you see that we're left with less and less of it. Getting up into the 2000s now, the Arctic is mostly filled with much younger ice. As we get right up to the present day practically, whoop, that's right, I've got some more to show you. You saw that in the end there was very little old ice left. It's okay. So just to revisit this, here's the end of winter in 1988 when there was lots and lots of that nice old ice. And here we are today with a little bit different color scale, but basically you see that there's hardly any of that thick ice left, or the old ice. And this is a big deal because, as I've said, the thick ice, it's a proxy for the ice thickness. And the ice thickness has a lot to do with how the atmosphere and the ice communicate with each other. And just to show you in another way, this is a plot of the ice thickness actually over just the last few years, and how the very thickest ice types have been declining. And there's the, okay. And that, as I said, is a big deal because the thinner the ice cover is, the more easily it can be melted. You remember I said before that when it was very thick, in a year you couldn't melt all that ice. There just wasn't enough energy coming from the sun or from the infrared radiation. But now that it's so thin, that actually can happen. It's also much more easily moved by the wind. It moves much faster now than it used to. And so as a result, it's much more likely to continue on this trajectory that we've been seeing of decreasing ice extent across the Arctic. And here's that ICESat data connected up with the previous estimates, and the color changes a little bit, but you can see just in the last couple years, the thickness of the thickest category, and then overall has just been dropping like a stone. So when people go up there to try to do research in the Arctic now, it's a lot harder because instead of having these nice big thick ice areas where you could actually used to be able to land a plane and they'd have ice camps that would last for years, now you go up there and it's just, they call it rotten ice. Big change. And just one more way to look at this. This is again a time series of the last couple decades, and the ice extent of the various thickness categories. This is in March, so this is at the end of the winter when you have the most ice in the Arctic, and you can see that the changes are mostly happening as loss of the oldest ice, but an increase in the youngest ice. But overall, there's not a huge change during the winter time. But in the summertime, overall, there's a large change. Again, you see that the oldest ice is disappearing, and that trajectory continues. Okay. So as I said, the thinner ice is much more mobile. It's much more vulnerable to any anomalies in the winds or in the amount of energy being transported up to the Arctic that could melt it. And in particular, there's this concept called the Arctic dipole, which is a high amplitude pattern in the winds, in the jet stream. And this is something that we've seen quite a lot in the last few years. And in particular, take note of 2007 and 2011. These are surface pressure plots here for the Arctic. Again, here's Greenland and Alaska over here. This Arctic dipole is characterized by having generally high pressure over on the Canadian side and strong low pressure over on the Eurasian side. And you can imagine that that sets up quite a strong wind flow that takes the ice directly across from the Pacific side all the way out and into the Atlantic. And during 2007 and 2011, these are the 2 years we had the record loss of sea ice. And you can see that this pattern is very, very strong. So remember, this is related to a high amplitude jet stream pattern, because we'll come back to that. And as I mentioned earlier, back in the good old days when that ice was really thick and we had a pattern like this, the ice just didn't respond because it was so thick that it didn't move very fast. And so it's much more susceptible to anomalies and wind patterns than it used to be. Okay. So we've lost all this ice, and as you know, ice is very white. It reflects most of the solar radiation that hits it right back to outer space. And so that energy never makes it into the Earth's energy budget. But now that we've lost all this ice, we have much more open water. The sun hits it in the spring and the summer. It goes right into the ocean, and it heats it up. So what we've seen in the last few years is a big change in the sea surface temperatures as a result of the loss of the ice, particularly we're over on the Pacific side here. Here's Alaska, here's Siberia. And this is the change in the sea surface temperatures in these areas as a result of the ice being lost and all this extra solar energy being dumped right into the surface of the ocean. So in 2007, when we had the most ice loss, and again in 2011 looks just like this, but I didn't have that in a graphic to show you, but it looks very similar. So a lot more energy being put into the Arctic Ocean. All right, so I'm just going to kind of summarize this story for you. Up in the upper right there is, again, those good old days back in 1979 in this case. And this represents in this time series here of the ice cover during the summertime, this period back in the 60s and 70s when the ice was relatively steady and the ice was nice and thick. So then the greenhouse gases started building up along with increased water vapor, more cloud cover, and this affected the ice, making it thinner and thinner. And then we had this attack of the positive AO, now working on a much thinner ice cover, and so it started this trajectory downward over the last, say, 70s to the 90s. And we know that thinner ice cover is more easily pushed by the winds, it's more easily melted by anomalous heat fluxes, and that results in a lot more open water that can absorb more sunlight, and it heats the ocean surface, which then feeds back and melts more ice. So this is what's known as the ice albedo feedback. You lose all that ice, you heat the water, that melts even more ice. So that brings us to where we are today. Down in this bottom right of this time series of the ice extent, it's being called a whole new state of the Arctic Ocean system. There's really no reason to hope that it might return to where we were before as the greenhouse gases continue to accumulate in the atmosphere. So what's up with all that heat? That's really the whole next section of what I'm going to be talking to you about, and this is all brand new research I've been doing just in the last several months, actually. So what happens to all that heat? Here's the Arctic Ocean, much warmer than it used to be. The fall comes, the air is getting colder. All of that heat starts to go back up into the atmosphere as sensible heat, as latent heat, so moisture, and also infrared radiation. And there's lots of it, much more than there ever used to be. So that brings us back to that question that I posed in the beginning, and that was not whether sea ice loss is affecting large-scale circulation, but how can it not? So the questions that come out of that, though, are how exactly is the atmosphere going to respond? And there's been a whole bunch of research lately looking at that question. Most of these studies have used models or a few with observations, looking at general ways in which the atmosphere responds to having this heat source up in the Arctic. But the approach that I'm going to tell you about today is really focused on how what we're calling Arctic amplification, which is the fact that the Arctic is warming much faster than the hemisphere in general, about twice as fast as a matter of fact, and how that Arctic amplification is actually causing extreme weather to change in the northern hemisphere, so down here where the people live. Now I want to be very clear about what I mean by extreme weather in this particular study, and that is the types of extreme weather that results from very persistent weather patterns. So things like drought, when it's dry for a long time, or flooding, lots of rain, that just, the weather patterns just get stuck. Cold spells, heat waves, that sort of thing. So and we know that those types of patterns are usually associated with very high amplitude jet streams, okay? So this is what we're talking about here in terms of extreme weather. And we can find examples for this as we look back in time. For example, if you take the 20 coldest days in Tampa and you look at the 500 millibar heights, the anomalies in the 500 millibar heights, and what you see is a very high amplitude pattern, a big ridge over the western US, a big trough in Florida or down over the east coast, and that brings all that cold air down to Florida. So a very high amplitude jet stream pattern. Same for the hottest days in Atlanta. Big ridge parked over the Mississippi Valley that leads to high temperatures down in the southeast. Or another example, the wettest days in Chicago. Again, big trough over the high plains, brings all that warm, moist air up towards Chicago, resulting in very heavy rains in that area. So it's these very high amplitude jet stream patterns that we're talking about here. Okay, so let's go back to all this heat we've got stored in the Arctic Ocean, and it's being released back up to the atmosphere. And how do we see that manifest itself in the atmosphere? Well, we're looking at actual observations here, or reanalyses, close enough, and looking at how the near surface temperature anomalies, or this is actually 1,000 millibars for the years from 2000 to 2010 during the fall. During the fall is when the cold air moves back into the Arctic, and all this heat starts to be released back into the atmosphere from the ocean. And you can see these really large temperature anomalies right in the areas where the big ice losses were. So over in the Pacific sector here and down over towards the Atlantic sector here. And the temperature anomalies are in the neighborhood of, say, 3 to 6 degrees. They're really large. So it used to be that people thought that the way that the surface of the Arctic Ocean and the atmosphere communicated with each other really only happened in the boundary layer, because the Arctic is characterized by having very strong surface temperature inversions most of the time. So that tends to cap that energy or the interaction to the lowest layers of the atmosphere. But what we're seeing now is very different. If we look now up at the 850 millibar level and we expand the view a little bit, so now you can see all the way down to the States and some of Europe, these temperature anomalies are extending over the whole Arctic basin. They're extending up to 850. If we go even further up to 700, you see that those temperature anomalies are still there. And if we integrate all that heat over the lower troposphere and look at something that we're all very familiar with, the 1,000 to 500 millibar thicknesses and the anomalies in those over the last decade or so, there's just really huge anomalies over the Arctic as a result of this sea ice loss. So that's in the fall. But we also see them continuing on into winter. It's not quite as Arctic, pan-Arctic, but for the last 10 years or so, it's manifested itself as a big thickness anomaly, positive thickness anomaly over the North Atlantic. And this is a signature that's very reminiscent of a negative NAO type pattern.
So how do you know that you can attribute this, being that such a short time scale of just 10 years, how do you know that you can attribute that to greenhouse gases and the whole climate change issue, and that it's not just part of some shorter term natural variability?
Well, I think you'll see as I show you some longer time records of change. This is really just to illustrate how the atmosphere is responding just in this particular decade. I'm sure if I picked a different decade, it would look a little different, but during this particular time period, 2000, 2010, when we've had these huge ice losses, it's a big signal, so it's something that we can look at. I mean, I think there's really no question that the ice loss is related to greenhouse gases, and I think it's a pretty direct connection between ice loss and what we're seeing in the temperature anomaly. So, you know, if you believe A equals C, knowing that A equals B and B equals C, then, you know, I can't say for 100%, but I'm pretty darn sure. Okay, so as we look at this thickness anomaly and note that it's largest over the Arctic, what this translates to is a change in the poleward thickness gradient, okay? It's warming more in the Arctic than it is in the lower latitudes, so that means the poleward thickness gradient is going to be getting weaker. And we can see this in the observations as well. This is some work that I did a few years ago looking at how the poleward thickness gradient is changing when you look at years that had less ice than normal in the summertime and compared that to years when there was more ice than normal in the summertime. So starting in the summer and comparing these two sets of years, you can see that the low ice years progressing into the fall and even into the spring, this poleward temperature gradient is weaker, and it stays weaker all the way into spring compared to years when there was more ice than normal. That's in the North Atlantic sector, and the same sort of pattern shows up in the North Pacific. Once again, weaker poleward temperature gradients or thickness gradients when the ice is lower in the summer. Yeah?
Just looking at that, the graph of the poleward 1,500 millibar thickness gradient, it seems like that in February and March, the difference between high ice and low ice years is much larger than, say, in November, December. Is that a correct interpretation?
Well, that's what that shows. And I have to let you know that there aren't that many years in each of those groups. There's only like 4 or 5 in each group.
Okay.
And so I think the takeaway message is more that it just stays lower and not so much that the difference is greater in the spring than in the fall. Because actually, the difference should be bigger in the fall. It just turned out that these particular years, through natural variability, you know, interannual variability, that it just worked out that way. So I don't think that's an important distinction there. Any other questions? All right. So now we want to try to start connecting the dots between this big change that we're seeing in the Arctic and how weather patterns, and in particular extreme weather, is changing in the mid-latitudes. So I'm going to focus on fall and winter. Okay, so we've seen that the thicknesses are increasing more at high latitudes than they are at mid-latitudes, and hypothetically or theoretically, we expect to see 2 main effects, or I expect to see 2 main effects. The first one is one that's well known by all of us, that this poleward temperature gradient is really what drives the jet stream. If we have a weaker poleward temperature gradient, we expect to see weaker zonal winds, okay? Do we see that in the observations? Yes, indeed. So if we look at, I'm going to focus in here on the region over North America and the North Atlantic, and what I've plotted here again is this poleward temperature gradient for each season. So the fall is in the brown, we've got winter in the blue, and spring in green, and summer in red. Going back to 1950, so this is going back in time quite a ways, And what you can see, especially in the fall and winter, is that starting around the 80s and the 90s, right when the sea ice really started to decrease, we see that this poleward thickness gradient has decreased dramatically. And along with that, if we look at the zonal mean wind speeds at 500 millibars in mid-latitudes, we can see that in the fall and winter, right about at the same time period, starting around the 1990s, big drop in the zonal wind speed, so the west to east winds, and this is at 500 millibars. And in fact, that difference just in the last few decades is on the order of 20%. That's a big drop in the wind speeds.
And this is Atlantic, not hemisphere?
This is over North America and the North Atlantic, and I'm going to do a lot more analysis in this area, so I'm kind of focused on that for most of what I'm going to show you. So, these weaker zonal wind speeds that we know, if you think back to your dynamics class in meteorology, how weaker zonal winds are related to the Rossby waves, which are the north-south waves that you see in the upper level flow patterns. Weaker zonal winds lead to slower moving waves, and that is we know when those waves move more slowly, the weather that we see at the surface is more persistent, because those waves are what determine what's going on at the surface. So if they're moving more slowly, the weather patterns are going to change more slowly or get stuck. And this, we've heard a lot about stuck weather patterns lately. It seems like it's happening more frequently. All right, that was the first effect. The second effect, I want you to think about a particular isopleth of the 500 millibar height field. So just, 560 or whatever your favorite 500 millibar height is. We've got these typical waves. This is just a schematic of a wave in the 500 millibar height field. And as we know that it's warming much more up in the northern section of the world than it is down in the mid-latitudes. So what we'd expect to see happen as a result is that in the northern part of these waves, or the tops of the ridges, would expect them to elongate northward because it's warming more than it is down here. It is warming some here too, and that's why the troughs are moving northward a little bit too. But we expect to see the ridges elongate northward. And what does that do? It causes the amplitude of the waves to increase. So the waves in the jet stream should increase as a result of this. And we know that higher amplitude waves progress more slowly. So this is another effect that is again causing the waves in the upper level flow or the jet stream to move more slowly, which again leads to more persistent weather patterns. Okay, so now is that really happening? We're going to look at a little more analysis that's going to illustrate what's happening according to the reanalysis anyway. So the way I've gone about getting at this is, again, focusing on the 500 millibar flow. I like the 500 millibar heights because they're nice, they're well behaved, the reanalyses capture them well. Satellites provide a lot of information to the reanalyses, so we have good confidence that they're real. And what I'm going to do is select a particular isopleth in the 500 millibar flow for each season, a different one for each season, but the goal is to capture the shape of the 500 millibar flow. So here's a case where I've selected this is just a random day just to illustrate it, but pick a narrow range of heights in the 500 millibar height field and subset out just those heights in the reanalysis that capture the shape of the pattern in the 500 millibar heights. So I do this for every day, and we're going to look at these subsets of the 500 millibar height field, okay? And see how they vary in time and space. Okay, so we're trying to find out whether this idea that the ridges are elongating and the waves are actually getting higher amplitude is really happening. So once again, just to remind you that we're talking about just one isopleth in the height field. And the way I'm going to go about measuring the wave amplitude is just talking about fall now. I'm going to look at the maximum latitude and the minimum latitude on each longitude line and how that difference is changing over time. So this is a way of measuring the wave amplitude. Basically, you're taking the highest ridges and the lowest troughs, taking that difference and using that as a wave amplitude measurement. And this is what we get. Only one other person has seen this plot besides you. It's brand new. So this is a Hofmeiler diagram, and it's the entire longitude range around the northern hemisphere. So this isn't just what I'm showing here. This is actually the whole northern hemisphere. And going through time, the colors here are showing this latitude difference or wave amplitude and how that wave amplitude is changing in time. Now that's a noisy plot. But if you actually calculate the trends at each longitude, that's what's shown up here. So in the fall, this is the 0 line going across here. So everything above that line means that there's an increasing trend in the wave amplitude. The red asterisks are statistically significant trends. So what we see is that just about everywhere around the northern hemisphere, the wave amplitudes are increasing during the fall.
What did you say about the statistically significant trends?
The red asterisks on here are showing where the statistically significant, or where the trends are statistically significant. Okay.
With your label, are you going eastward from Greenwich Mean Time there? Or you're with
Yeah,
your latitude lines?
So, yeah, so 0 is at Greenwich, and then it goes around towards the east. Yeah. Sorry about that.
Jennifer,
Yes.
does this, excuse me, does this mean that this is showing evidence that northern hemisphere synoptic scale systems are stronger if you have an increase in wave amplitude?
Not necessarily,
Okay.
because it doesn't describe the baroclinicity, for example. It's really just describing the shape of the waves in the 500 millibar flow, 500 millibar pattern.
Have you thought of looking at the meridional component of the wind?
Yes,
To
and
use it?
that is in future research where we already started. We've developed a new index of the meridional flow that would show how the meridional component is related to the total wind speed.
All right, it seems like that would be more indicative as opposed to just the amplitude itself if there's a decrease in the gradient.
Well, I think it would show two different things, or they're complementary for sure. And that's just something we haven't gotten to yet, but I agree with you. Yep, that's something that we plan to do, and not just with reanalyses, but also with models, and looking forward into the future. Any other questions? Okay. So now we're going to go back to this region here over North America and the North Atlantic and spend the rest of our time talking about that area and look at how these patterns in the 500 millibar flow are changing, and again, just continuing with autumn now. So this is another way to look at what's happening. I call these my fire plots. They sort of look like flames. And what this is showing are fractional anomalies. So it's departures from normal of the numbers of these grid points at each latitude. A value of 1 means that there's the normal number compared to the first 30 years of this record. So the red colors then mean that there's an increase, and upwards, if some of these colors are getting up near 2, that means there's twice as many as you would find normally. So what we see when we look at this fire plot is that ridges are increasing north of 50 north. We're seeing an increase in the ridging. But at the same time, we're also seeing these blue colors down in the bottom there, the troughs are decreasing. So just by that, it's hard to know for sure whether the wave amplitude is increasing or whether the whole pattern is just shifting northward. So we can get at that with this next analysis. And that is, we look at just the maximum latitude of these grid points. So basically picking off the ridges, all right? And looking at how the maximum latitude is changing over time. Starting back in 1960, you can see there's a very steady increase in the latitude of the peaks of the ridges over time. And I've also plotted on there, in a reverse scale, the September sea ice area, just to give you a visual comparison on how these two quantities are changing pretty similarly over the last few decades. And in fact, the correlation coefficient is quite high. That's that R equals minus 0.8. It's pretty high correlation between those two. So we see the maximum latitude of ridges increasing. This is the southern extent of the troughs. And you can see they're actually staying quite steady over the last few decades. And then the difference between those two is another measure of the wave amplitude. And that has also been increasing over the last few decades. And again, it's pretty highly correlated with the changes in the sea ice in the summer. All right, so when you start thinking about how actual weather patterns might be changing, you want to know where these ridges might be increasing, where the troughs might be changing. So we're going to, again, look at our Hofmeiler diagrams, but in this time, we're just going to pick off all the grid points that are north of 50 north. And if you think back to that fire plot, and it showed how the ridge points were increasing north of 50 north, we're going to pick those points off and see where they are occurring in longitude. So this is, again, just this section of the world here. So longitude on the x-axis, time on the y-axis, and the colors here now are the numbers of grid points that are north of 50 north. So it's kind of interesting. We see that the peaks in the ridges have a very preferred set of longitude areas where they tend to occur. They tend to be mainly over western North America, which makes sense. That's where we expect to find them in the fall, and also in the eastern North Atlantic. And if we do, again, calculate the trends in the changes in these ridge points, if you want to think of them like that, we see that they're increasing almost everywhere. So here's the 0 line again, and everything above that means that we're getting more ridge points north of 50 north. But again, the statistically significant ones are indicated with those red asterisks. And interestingly, those seem to be occurring mainly just west of Greenland, which might be of interest to Jim. So as we see these ridges increasing over North America in general, you have to wonder whether it might somehow be tied into the increasing extremes in temperatures that have been observed recently as well. So this is from the NOAA Climate Extremes Index and the temperature maximum extremes and how they've been increasing over the last couple decades, as well as the temperature minimum extremes. And I can't tell you for sure whether they're connected, but circumstantial evidence. All right, so that was fall. Now we're going to do the same analysis, but for winter. In winter, we take a different selection of the isoplethe, but the goal is to do the same thing, is to capture the shape of the 500 millibar pattern. So we look at our fire plot for winter time now, and it actually looks very similar. We see, again, lots of increasing ridges north of 40 north, and also decreasing troughs down in the southern latitudes. And again, we're not sure whether this is because the wave amplitude's increasing or whether the whole pattern's shifting northward. But again, we can get at that by plotting how the maximum latitude of the ridges has been changing over time, which is this blue line, and we can see that it apparently is increasing steadily over time. And I've also plotted on there the AO index, because there's been some suggestion that perhaps the changing patterns are related to the AO index. In fact, Dan talked about that quite a bit on Tuesday, and I'm going to get at that a little more in a second. But you can see that it appears that the AO index and this increasing latitude of the peaks of the ridges are not very closely related. In fact, the correlation coefficient is quite low. The troughs are also moving northward, and the latitude difference is again increasing, suggesting that yes, the wave amplitude is getting larger. So after Dan's talk, I put in this another graphic here showing how the December AO index has been changing over time, starting back around 1950. And this is really interesting because I didn't notice this before, but the volatility of the AO seems to be increasing quite a lot as we go through time. You can see the big negative AOs of the strong winters of 2009, 2010, and 2010-11, and you can also see just this past December how we had this very extreme positive AO. And one of the thoughts that has been suggested is that somehow the solar output might be related to the AO, and it may be, but if you look at the sunspots, which are related to the amount of ultraviolet radiation that the sun is putting out, which is part of this theory, and how that lines up with what the AO is doing, there are times when it seems to line up quite well. In fact, those two times it lines up quite well. Then there are other times when it doesn't line up very well at all. So I think just based on at least these few data here, and I haven't calculated the correlation coefficient, but it doesn't seem like sunspots is a good explanation for how the AO is flipping back and forth.
Hey, Jennifer.
Yeah.
Before you take that off, I looked at the same plot, and volatility struck me in two ways. One is the amplitude seems to be changed, but it also doesn't seem to be staying in any one pattern for
Right.
more than a year or two before it flips off into another direction, which is very different than what we saw in the 50s and 60s.
It is. It's really interesting, and I hadn't looked at this before I found this plot, and I don't have an explanation, but it is a really interesting change that we seem to be seeing.
Yeah, and I guess if that pattern continues, the predictability, particularly using the AO, goes down.
Yeah, that would be my conclusion too.
You say predictability of what? Specific weather? Local
Yeah,
weather?
particularly for the seasonal forecast.
Oh, for seasons.
Yeah, it's going to make it tough. Okay, so getting back to our winter analysis here. Again, we're going to look at how these changes in the ridges are occurring in longitude. That helps us understand how the actual weather patterns might be affected by these changes. So again, we've got longitude here and time. These colors are related to the number of grid points in the ridges. And you can see once again that the ridges during the winter time are have very preferred longitudes where they like to line up, in particular over western North America, which we know that makes sense. We tend to get big ridges over the west, and also the eastern North Atlantic. So how are these changing in time in terms of trends? Once again, we've got the 0 line here, so everything above that 0 line means that the ridges are increasing in time, and the asterisks showing you where they're statistically significant are especially over North America in the wintertime. So what it's saying is that we're just getting a whole lot more ridging happening over North America in the winter. Now we can flip this around and do the troughs as well. So if you remember back to the fire plots, how it looked like there were decreasing troughs in the lower latitudes. So what we're doing now is we're picking off all these grid points that are south of 40 north and looking how those are changing in time. So now our Hofmeiler diagram is showing how these points in the troughs are changing. And it's a very interesting looking pattern again. These troughs tend to be lined up right along the east coast in the winter, which makes sense to all of us meteorologists. And as we look at the trends, this time we're seeing that the trends are all negative. The zero line is now up there. All the values are below the zero line, and they're statistically significant, especially over the west central U.S. and over the eastern North Atlantic. So what we're seeing then is that the troughs over western North America appear to be either getting fewer in number or weaker. Okay, so that was the cold season, the fall, and the winter. What about summer? So the summer's a whole different ballgame because the sea ice is really not playing a role anymore. But as we talked about somewhat yesterday, the timing of the snowmelt over high latitude land has been changing dramatically through time. This is an example of the snow cover anomalies during May. This is from the Rutgers Global Snow Lab, showing how in May the snow anomalies are getting more and more negative. It looks just like this for April. It looks just like this for June. So as you melt that snow earlier, what you find is that it allows the soil to be exposed to the sun earlier. That soil dries out, that soil warms up, and that then we can heat the atmosphere over the high latitude land areas. And this is showing the temperature anomalies for the near surface air for the last decade or so, and how these temperature anomalies are pretty much lined up over the areas where the snow has been disappearing earlier in the spring. So this extra warming over high latitude land is adding to the Arctic amplification, or the enhanced warming over the Arctic relative to the northern hemisphere. So just quickly, we're going to do a similar analysis for the summer. And what we see then is if we look at the ridges, this maximum latitude of the grid points, we see that there's a very definite increase, just like in fall and winter. And I've plotted on there in a reverse scale that May snow area, and you can see that just visually they seem to be tracking each other pretty well. In fact, the correlation coefficient is very high. We see that the troughs are also increasing in latitude, and the latitude difference between the two, or the wave amplitude in the summertime, also appears to be increasing. And all of those are pretty highly correlated with the changes in the snow cover. If we look at the Hofmahler now, where those ridges are changing most, north of 60 north. And you can see that, again, in the summer, the ridges tend to be lined up in a preferential area over western North America, which all makes sense to all of us. And if we look at the changes in those ridges, we see that the trends are positive everywhere, once again. So everywhere the ridges are extending farther northward, and particularly in the western North Atlantic. So this area of the statistically significant increasing ridges is sticking up right at Greenland. And we know that there's been a lot of warming in Greenland lately, which Jim's going to talk to you about in just a little while. And I think this might have a role. And I forgot to mention something. I'm just going to jump back to the winter for 1 second. Go back to the troughs in the winter. Okay. It's like I forgot to mention the Arctic paradox, which is kind of where this all started. So remember, the Arctic paradox came up because of those very cold, snowy winters in the Northeast and in Europe in the previous 2 winters. And as we look at these troughs and the Hofmahler of the troughs, they show up right here. That enhanced color there, and these increased number of troughs over in Europe. So when I look at this, those don't look like they're that unusual to me compared to looking back through time at where the troughs have lined up. We see there have been other periods when there's been a lot of troughing over the eastern U.S. You know, maybe what we're seeing over Europe is something unusual because you don't see that very often, but I think we'll have to see how things unfold in time. But just based on this information, I'd say that the Arctic paradox is really not a paradox at all. It's just happened to have a couple cold winters. That would be my assessment at this point. Okay, so let's get back to okay. So, as I mentioned in the summer, this general increased ridging. And so you have to ask whether that might be related to the increasing temperature maxima and temperature minima that have been observed in the summertime over the U.S. Very definite increasing, especially in the minima. Can't say for sure whether it is, but it certainly is consistent with what we're seeing in terms of the changing ridges. Okay, so I'm going to pack this all up into one summary slide, one schematic for what I think is happening. We know Arctic amplification is happening. It's warming about twice as fast in the Arctic as it is in the rest of the northern hemisphere, especially in the fall and winter, but also, as I've shown you, in the summertime. This leads to a weakening of the poleward thickness gradient, which I showed you. And this has two effects. One of the effects was the weaker upper level zonal mean flow. We see this is happening in the reanalysis, in the observations. We know this is related to a reduced phase speed of Rossby waves. The second effect is this elongation of the ridges northward. And I've shown you that this seems to be happening as well. And that tends to increase the amplitude of the waves in the upper level flow. Now, both of these effects are doing the same thing. They're both causing the Rossby waves, or the north-south waves in the upper level flow, to progress more slowly. Both of these things contribute to that. And we know that when those Rossby waves or upper level waves move more slowly, the weather conditions at the surface change more slowly as well. The weather conditions are more persistent. The weather patterns get stuck. When you get patterns that don't change very fast, this leads to an increased probability of certain kinds of extreme weather. Things like cold spells, heat waves, flooding, prolonged snowfall, and drought. So this is what I'm calling the revenge of the atmosphere back on the sea ice. But there's more to the story, I think, because as you increase the wave amplitude, you're also going to feed back to the sea ice. Remember back to those, the Arctic dipole caused by a high amplitude flow. Well, that tends to reduce the sea ice. And so the atmosphere's got the last word, getting back to the ice. That's what I have to tell you about. And I think we've got some time for questions, if there's any questions from anybody that's not in the room or any more from in the room.
Jennifer, thanks very much. We do have questions in the room, so we'll go ahead and take those and have a little discussion if that's something that develops. We also have some questions online.
Cool.
So we can take those questions as well after we're done with the discussion in the room. John?
Hi, Jennifer. John Morales from NBC Miami. So, as I looked at the persistent ridge in the western U.S., stretching up towards Alaska, troughiness across the eastern section of the U.S., I couldn't help but think of the recent years where the trough along the east has pretty much saved much of the U.S. from strikes from
Hurricanes, yes.
So I'm wondering, does your research suggest that this is the type of pattern that could be quite persistent for years to come?
It appears, the trends are calculated over that whole time period. And so it's possible. It's possible. Part of what we're going to do into the future, as I mentioned before, is look at model projections and see whether these types of patterns are captured by the models looking back in time, but also how they're going to continue to evolve into the future. As we know, greenhouse gases are going to continue to accumulate in the atmosphere. We expect the sea ice to continue to decrease, maybe even disappear in the summer by the middle of the century or so. So I think the indications are that, yes, these trends could continue and maybe affect things like, where hurricanes go.
Dale Eck from the Weather Channel. What John's question was, and it's interesting that as you think back to some of the tropical seasons, and and it might relate to some of this, you get more persistent patterns, if you will.
Mm-hmm.
And it seemed like if you look at what's been going on since 2000, obviously a couple of years, especially 2004, where you had this persistent ridge in the Atlantic, and it just kept funneling all these tropical waves into the southeast U.S. So it wasn't a case of where you go through a season, and even this last season, you're going along, you're going, well, for a while, it looks like nothing in the foreseeable future. We got the trough, da-da-da. You got this one little window where we got, what's her name, coming up through the eastern, Irene.
Irene, yeah.
But then the pattern just was persistent over
Mm-hmm.
much of the season, and especially the peak of the season, which you really only have 6 weeks to make it happen. And I think, even what we had last winter, it was very persistent because of the negative NAO, that we had the consistent storms and cold winter in the east, and then this winter it was different. It's been a persistent pattern that has kept it relatively mild across the United States. So
Yes.
I think what we have been seeing in the synoptic world is indicative of what her research is saying.
Right, that was the sound familiar part. It really does seem like that's what's going on. Yeah, it's like,
So I'm sure in history, in the historical record, there have been times of low sea ice in the Arctic, centuries ago, millennia ago.
you'd have to go back thousands of years.
Okay, how
to
did the
find-
sea ice recover? Or do we know?
Well, I think back in those days, the climate was changing because of orbital changes, and then that set off positive feedbacks in the system. You start warming the planet, and more CO2 is emitted from things like melting permafrost, and so. But we know that back then it was because of changes in the orbits, and the models capture those very well.
Because it sounds like the feedback back loop you're talking about, even without an increase in CO2, would still continue to produce sea ice melt.
It would contribute to that, but if you did get somehow some big shift in the weather patterns that brought a lot more cold air into the Arctic, it would probably win, because those feedbacks work both ways.
Mm-hmm.
Once the Arctic amplification works in a warming mode and also in a cooling mode. If you look back in time, the Arctic has much higher fluctuations in temperature than the Northern Hemisphere as a whole. So it could turn around, but as we're changing the composition of the atmosphere, it would be pretty hard to do.
Jennifer, a friend of mine, Stu Oster at the Weather Channel, has been subjectively collecting records of 500 millibar heights in the high Arctic. And I noticed, and just kind of a comment, that I think they set an all-time record in Alaska and in Greenland over the last couple of years up there.
Record highs.
Record high heights. I think I saw something in the late fall of the 580s. I believe it was in Greenland, and Jim might know more about that.
Yeah, well, that hooks right up with the thickness anomalies that I showed, because that's all bumping up the 500 millibar heights.
And an additional question here: has anyone looked at on whether or not we're seeing an increased number of cutoff highs, cutoff lows over North America? It would seem to follow along from the increased amplitude in these troughs, where they would collapse over into a cutoff.
That's interesting, because the whole blocking pattern. People have tried to look at whether blocking patterns have changed over time, and it hasn't been conclusive. And that's why I decided not to look at blocks, because I think there's more to the story than just blocks. You can have these high amplitude patterns that result in extreme weather, or just they're just different patterns, and there's probably going to eventually be a signal in the blocking patterns as well. But right now, I think just looking at how the amplitude of the waves is changing is more indicative of, or certainly it's given us a better signal of what's changing in the last few decades. But I think that's probably going to emerge.
Thanks, Dave. Two questions for you. Have you looked at thermal expansion of the Arctic Ocean with a warming ocean, and whether or not it's actually covering more real estate up there. And you know, skeptics would say this is all great, but the satellite record only goes back to 1980. And how do you respond to that?
Okay. First, the thermal expansion of the Arctic Ocean. That heat that I showed and the surface temperature changes of the Arctic Ocean are really over a fairly shallow layer, because the Arctic Ocean is very strongly stratified. There's a layer on top of the Arctic Ocean that's very fresh, and that sits on top of a much warmer layer of ocean that is actually water that's been coming in from mostly the Atlantic and also from the Pacific and to some extent. But that fresh layer of water is really the only part that absorbs the energy that is being absorbed because of the ice disappearing. So the heat capacity of a shallow layer is just not that high. So the thermal expansion is probably not a huge factor. I'm not an oceanographer, but that would be my gut reaction. Otherwise, as far as the satellite records going back in time, certainly that's an issue with the sea ice records. We don't have the detailed ice edge that we have now with satellites, but as I mentioned, there's been a lot of shipping up there, a lot of fishing, a lot of whaling, and they took very detailed measurements of the ice edge back then because it was very important. They didn't have GPS, they didn't have internet telling them where the icebergs were, that sort of thing. So it was really important for them to know where the ice edge is. So going back a ways, and of course the aircraft came online after World War II, so they had a lot of air reconnaissance of the ice and so forth. So I think you can go back pretty far and have pretty decent estimates of the ice. As far as the atmosphere goes, one of the nice things about the 500 millibar is that balloons get up that high. So even before we had satellite sounders and GPS sounding information, there's a lot of weather balloons over the North America for sure. Maybe over the North Atlantic it's a little spotty, but I think the 500 millibar fields going back pretty far are pretty reliable, especially for these large-scale features like ridges and troughs.
Jennifer, one of the things that I'm really interested in, and I know this is not your specialty, but maybe we can talk about it a little bit. Jennifer and I are on a committee, the Polar Research Board, it's a committee of the National Academy of Sciences, and one of the things that we've been talking about is what happens to ocean circulation when you get into a situation where you've lost the sea ice. And I don't know that we know a whole lot about that. It's one of these feedbacks that could keep the Arctic ice free. It could, we don't really know.
Mm-hmm.
But I think that's something that we all need to keep an eye on. There's an ocean connection here,
Sure.
particularly from a circulation standpoint.
Mm-hmm. Yeah, and there's evidence that there have been increasingly warm pulses of warm water coming in from the Atlantic. But as I mentioned just a minute ago to Matt, that Atlantic water is really sequestered from the ice because of this very stable fresh layer that sits on top of the Arctic Ocean. And so even though there's all this extra heat floating around down under there, so far anyway, it hasn't made contact with the ice, and it hasn't had an important impact on the melt of the ice.
Jim White, University of Colorado. I would say that in some areas where the warm water has been coming in, it has a huge effect on the ice sheets and ice melting. This is
Right.
probably has more impact on lubricating
Yep.
the bottom of ice sheets and making ice flow off the continents faster than the air warming does.
Right. Well, Greenland is more exposed to the surface waters affecting its glaciers, and we do see an increase in the sea surface temperatures affecting especially the wintertime ice edge in the Atlantic. And so a lot of the decline in the winter ice edge is because of increasing sea surface temperatures in the North Atlantic, where it butts up against the winter ice edge. So it is playing a role for sure.
Jennifer, I just have a question. This is Dave Jones. You showed that fascinating loop of the older ice kind of being flushed out of the Arctic. Can you just explain again just what the significance of losing older ice is versus just having ice form seasonally?
Right. So that thick ice, that older ice, is much more stable. It's not as affected by any natural fluctuations in winds or, you know, a big shot of warm air coming in from the south, from the Pacific, say. It's so thick, and it's also very compact. And so it just takes a whole lot more to move it and change it. And so if you now have an Arctic Ocean that's mostly covered by much thinner ice, it's much more loosely packed, you can melt that much ice. It's only like a meter thick. If you have a big flux of warm air and moisture coming in from the Pacific, which is what happened in 2007, it melted a whole bunch of ice. And that just couldn't have happened when the ice was really thick. So not only is it more vulnerable to any kind of a melting situation, but also the winds can move it. I mean, the ice is moving about twice as fast now than it used to.
So when someone might come up and say, look at the extent of the Arctic ice, it's back to normal, how do you react to that?
Well, you know, every winter it grows. And, you know, sometimes people will come on and say, those guys don't know what they're talking about. Look, it's growing again, and it's right back almost where it used to be in the wintertime. Well, yeah, it grows in the winter. It's still going to get cold up in the Arctic. Even if we lose all of the summer ice, we're still going to have winter ice. So extent is not the whole story, and that's why these newer measurements of ice thickness are so important, because really that helps us get to the ice volume, which is really affecting things like the freshwater content of the Arctic Ocean, what happens to that fresh water as it maybe enters the Atlantic. So it's really, the ice volume is a much more important variable than the extent for some things, although the extent is really important for things like the albedo of the Earth. You know, the more ice you have, the more energy is going to get reflected back to space. So they're both important, but for different reasons.
NASA's put out some good graphics at the end, in I think September, of the minimum extent of the sea ice in the summer. So then that kind of shows you what survived,
Right.
and what has a chance of becoming old ice.
Exactly.
And there's not a lot of it there. Back to your Arctic paradox phrasing, though, I think that's a good one for us, because as broadcasters, we get questions from the public saying, hey, with global warming, how come it's so cold, especially the last 2 winters in the east? And so, you know, to be able to try to explain it like, well, just a warming atmosphere is leading to colder weathers that's lasting a longer time in some areas is valuable, I think, to the general public in terms of understanding.
And I think in some areas is really important because, you know, the waves, your weather is governed by where you are relative to these upper level waves. And, you know, if the trough sets up over the east, then of course it's going to be cold in the east, but, you know, it might set up somewhere else. And so you could have a different persistent pattern still for the same reason, but it's just, you know, in a different place. But good, I'm glad you got something to take home with you.
So just back to the thickness issue, I think it is worth pointing out that, you know, back in the 60s, for example, much of the Great Lakes froze every winter.
Mm-hmm.
And this is something we've looked at in this group before, but that ice can go away in a matter of 2 weeks.
Right.
And it's seasonal ice. And
Yep.
it's just a question of, as you were pointing out, it's not thick enough to survive against assault from warming below, warming above, and then the winds take it over.
Right.
So the seasonal ice is much more subjected to going away very quickly.
Right. And we have much more seasonal ice than we used to. It's becoming more Antarctic-like. I mean, most of Antarctic ice is seasonal ice, and that's why it all disappears every summer, almost all of it. There's just one section that has some thicker ice. But so the Arctic is becoming more Antarctic in a way, just based on the type of ice that's there.
Dan Satterfield, Huntsville again. Can you talk about where we stand with the satellite monitoring? I know, didn't we lose a sounding unit off one of the satellites? Some of them are aging that monitor the ice. Are there some new satellites coming online that are going to help here? Where do we stand?
You know, I haven't been keeping track of that situation. I know we're not in as good shape as we should be. You know, satellites are so expensive. I think in terms of the ice cover, we're in pretty good shape because the passive microwave sensors are actually military sensors, and I think they're probably not going to take those away. And those are the ones that we use mainly for tracking sea ice.
And is the sub-data still being used, or is that pretty much gone?
No, it's definitely still being used. And in fact, they just released a whole new data set of submarine ice data at the National Snow and Ice Data Center. I just got an email about it yesterday, as a matter of fact. So it's a very useful data set.
So let me put my paleoclimate hat on for a second. I got one on. One interesting thing that we have not looked at, we might want to look at in this conference, is that during the mid-Holocene, about 5,000 years ago, when summer insolation was higher, there was, we think that the Arctic sea ice was much less, particularly in the summertime. And it might have actually been more or less ice-free during bits of the summertime. The weather patterns at that time, as best we can tell, were quite, were different than today. This is a time when there was dune formation, for example, in eastern Colorado and Great Plains, and very large droughts in the western United States. And it might be worth going back to that, and what you've done here, I think, is make a connection between the sea ice story and the larger hemispheric climate picture. And maybe it's time to go back and look at what the hemispheric climate was like, particularly North America, and compare that to an ice-free climate time. So that's something we should talk about.
Might be a good analog, yeah.
Okay, Jennifer, we have a question from an online viewer, and I'm going to hand this over to Sarah Maxwell, and she can ask that question.
Hi, this comes from Bob Berwin. He, again, is a local here in Frisco, Colorado. And he asks, can you detect or would you expect the amplification, I think where he's referring to the synoptic amplification you were talking about earlier, to ease as the sea ice reaches maximum thickness in the late winter?
Well, it really all depends on how quickly the heat that was dumped into the atmosphere is lost to space and redistributed throughout the northern hemisphere. I mean, we see that the effects of the sea ice loss continue well into the wintertime. And where you draw the line of, where it stops having an effect is a little tough, and it probably varies from year to year. But in general, yes, as the Arctic reaches more normal winter temperatures, if in fact it does, then you'd expect it to become a more normal type weather pattern, I would think.
We have another online question from Mike Collington. He's in St. Louis. He's just curious to know if the Arctic ice has ever disappeared and then reappeared.
Well, might have to rely on Jim for this one, but I know there is evidence that the Arctic has been ice-free in the past. I know it's a very long time ago, on the order of like 800,000 years. Something like that.
Seasonally, it was probably ice-free in mid-Holocene, and it probably was ice-free given that previous interglacials were warmer than this one. It may have been. Right. We don't know. It may have been ice-free at that time. It was. You have to go back about 3 million years before you get to the really ice-free Arctic conditions. But yes, it has been ice-free in the past.
Yeah, and obviously it's got ice now, so it recovered. But as I said earlier, those fluctuations in the past were due to changes in the orbital patterns of the Earth and changes in the sun and things that are not related to what's happening today.
Okay, and I just want to correct myself. Sorry, I pronounced his name wrong. It's Mike Collington from St. Louis. Any other questions in the room here?
I Googled ISAT, and ISAT-2 is scheduled for launch in 2016 to answer your question.
Okay, good.
Awesome. Well, for those of you watching online, we're finishing about 6 minutes before our break. So we're going to go to the agenda, and then we're going to be back here at 10:15 Mountain Time. So please stand by and stay with us. This was a fascinating presentation, Jennifer, with excellent graphics. Thank you so much.